Welcome! Today, we'll explore LeetCode problem number 1228, missing number in arithmetic progression. In this problem, we are tasked with finding the missing number from a sorted array that forms an arithmetic progression. We'll discuss the problem, analyze the approaches, and walk through the solution step by step. Let's dive in. This problem involves an arithmetic progression, which is a sequence of numbers where the difference between consecutive terms remains constant. Your task is to identify the single missing number in an array that is sorted in strictly increasing order and otherwise forms such a progression. The input is an array of integers, and its length will range from 3 to 10,000. Each integer in the array lies between -100,000 and 100,000. The output should be the missing number as an integer. It's important to note that the sequence will always have exactly one missing element, and there will be at least 3 elements in the array. This guarantees that the input is valid and adheres to the problem's constraints. For example, consider the input array 5, 7, 11, 13. Here, the sequence is almost an arithmetic progression, except the number 9 is missing. The common difference between consecutive terms is 2, and inserting 9 between 7 and 11 completes the progression. Another example is the array 15, 13, 9, where the sequence has a common difference of -2. The missing number is 11, which, when added, restores the progression. These examples highlight how the missing number can be found by identifying the common difference and determining where the sequence breaks. Now, take the array 1, 3, 7, 9, 11. Here, the progression has a common difference of 2, but the number 5 is missing. Without 5, the gap between 3 and 7 disrupts the sequence. Once 5 is inserted, the progression becomes complete. The constraints of this problem further clarify the requirements. The array length will always be at least 3 and at most 10,000. The integers in the array span from -100,000 to 100,000, and the array is guaranteed to be sorted in strictly increasing order. The problem also ensures that the common difference is non-zero and that there is exactly one missing number. Additionally, the problem guarantees the input forms a valid arithmetic progression with only one missing number. This means you don't need to validate whether the array follows the rules of an arithmetic progression, it already does, except for the missing element. By leveraging these guarantees, you can focus solely on efficiently identifying the missing number. Keep in mind edge cases such as the missing number being at the start or end of the array, a negative common difference, or very large arrays. Handling these efficiently will ensure your solution is robust and performs well under all scenarios. To solve the problem of finding the missing number in an arithmetic progression, we explored several approaches. First, there's the brute force method. The key idea here is that in an arithmetic progression, the difference between consecutive terms is constant. By iterating through the array, we can calculate this common difference using the first 2 elements. Then, as we examine each pair of consecutive elements in the array, we check if their difference matches the expected value. If we find a pair where the difference deviates, the missing number must be the value that restores the progression, which is simply the current element plus the common difference. While this approach is intuitive and doesn't require extra space, it's inefficient for large arrays because it involves a full traversal, even if the missing number is near the beginning. Now, a more efficient solution is the binary search approach. This leverages the sorted property of the array to narrow down the search space significantly. In an arithmetic progression, the deviation caused by the missing number will disrupt the expected positions of elements. To implement this, we first calculate the common difference using the first and last elements divided by the total number of terms. Then, using binary search, we repeatedly check the midpoint of our search range to see if the current element aligns with its expected value based on the progression formula. If it doesn't, the missing number lies in the left half, otherwise, it's in the right half. This process continues until the search range is reduced to the point where the missing number can be directly identified. The logarithmic time complexity of this method makes it highly efficient and well suited for larger datasets. Additionally, we considered a mathematical approach based on the sum formula of an arithmetic progression. The sum of the first n terms of an AP can be calculated by multiplying the number of terms with the average of the first and last elements. With this, the expected sum of the complete progression is straightforward to compute. By subtracting the actual sum of the given array from the expected sum, we can directly determine the missing number. This method is simple to implement and doesn't require iteration or searching. However, it has some drawbacks, particularly the risk of integer overflow in certain programming languages when working with large numbers. This potential limitation makes it less robust compared to other strategies. Among these approaches, the binary search method stands out as the most optimal for this problem. Its logarithmic time complexity ensures that it handles large arrays efficiently, and it makes excellent use of the sorted property of the input. While the brute force approach is conceptually simple, its linear time complexity becomes impractical for large inputs. On the other hand, the mathematical approach, though concise, introduces potential risks with integer overflow and can be harder to debug in edge cases. By choosing the binary search approach, we strike a balance between efficiency and practical robustness. It's fast, scalable, and avoids the pitfalls of the other methods, making it the most suitable strategy for solving this problem effectively. In this problem, we are given a sorted array that represents an arithmetic progression, but one element is missing. Our goal is to find that missing number efficiently. An arithmetic progression is a sequence where the difference between consecutive terms remains constant. For example, in the sequence 2, 4, 6, 10, the common difference is 2, and the missing number is 8. To solve this problem, we'll use an optimized approach based on binary search. The first step is to calculate the expected common difference, which we can compute using the formula last_element, first_element, divided by the total number of elements, including the missing one. Once we have this diff, we can leverage binary search to efficiently locate the gap in the sequence where the missing number lies. Using binary search, we systematically narrow down the search space to pinpoint the missing number. At each step, we compare the difference between the current element and the previous one to the expected diff. If the difference exceeds the calculated diff, it indicates that the missing number must be between these two elements. Otherwise, we continue searching in the appropriate half of the array. For arrays with only two elements, the missing number is easily found as the midpoint between the two. If no discrepancies are detected during the binary search, the missing number can be determined as the last element minus the diff. By using binary search, we achieve a time complexity of O log n, which is far more efficient than a linear scan, particularly for large arrays. Pre-computing the diff is crucial because it provides us with a consistent reference to identify irregularities in the sequence. When handling edge cases, we ensure that our algorithm works for scenarios such as a missing number at the start or end of the array, or when the array contains only two elements. It also handles arrays with negative integers seamlessly, as the constant diff applies universally to both positive and negative numbers. The input to this algorithm is the sorted array itself, and no additional data structures are required, making the space complexity O1. This simplicity in design ensures that we operate directly on the input array without incurring extra memory overhead. By combining binary search with the pre-computed diff, our solution efficiently identifies the missing number even for large-scale inputs. Now, let's walk through an example to see how the algorithm works in practice. Consider the input array 5, 7, 9, 13. First, we compute the common difference, 13 to 5, divided by 4, which gives us 2. Using binary search, we start by checking the middle element, which is 7 at index 1. The difference between 7 and 5 is 2, matching the expected diff, so we continue the search. Next, we check the middle element in the remaining subarray, which is 13 at index 3. This time, the difference between 13 and 9 is 4, which is greater than the expected diff. This indicates that the missing number lies between 9 and 13. By adding the diff to 9, we determine that the missing number is 11. Thus, the output for this example is 11. This code solves LeetCode problem number 1228, missing number in arithmetic progression, by efficiently identifying the missing number in a sorted arithmetic progression. The approach uses binary search, leveraging the sorted nature of the input array to achieve an O log n runtime. First, the common difference diff is calculated using the formula error-1 error0 /n, where n is the length of the array. This represents the expected difference between consecutive terms in the arithmetic progression. Next, a binary search is initiated with pointers left and right set to the start and end of the array, respectively. The goal is to narrow down the range to the missing element. At each step, the mid-index is calculated as the midpoint of the current range. If the value at ARR, mid, matches the expected value based on the arithmetic progression formula ARR, 0, plus mid asterisk diff, the missing number must be in the right half, so the left pointer is updated to mid plus 1. Otherwise, the missing number is in the left half, so the right pointer is updated to mid. The loop continues until left equals right, at which point the missing number is identified using the arithmetic progression formula ARR, 0, plus left asterisk diff. This approach is efficient and works for all valid inputs, including edge cases with small arrays or large ranges. The binary search ensures that the solution is optimal for large input sizes, making it suitable for competitive programming scenarios. This is the Java implementation for LeetCode problem number 1228, missing number in arithmetic progression. It mirrors the Python solution provided, using a binary search approach to efficiently find the missing number in the arithmetic progression. Key differences include Java's explicit type declarations and the usage of integer division when calculating the common difference. The logic ensures O log n complexity for identifying the missing number. To solve this problem, let's start with an example, the array 5, 7, 11, 13. First, we calculate the common difference of the arithmetic progression. The length of the array, n, is 4, and the difference, diff, is calculated as the difference between the last and first elements divided by n. So, 13 to 5, //////4 is equal to 8 ////4 equals 2. This tells us the common difference in the progression is 2. Next, we initialize variables for binary search. We set left to 0 and right to n1, which is 3. Now we are ready to start the binary search process to locate the missing number. In the first iteration of binary search, we calculate the middle index, mid, as left plus right, // 2. Substituting left equals 0 and right equals 3, we get mid equals 1. Now we check if the value at ARR, mid, matches the expected value based on the arithmetic progression. Here, ARR, mid, is 7, and the expected value is ARR, 0, plus mid asterisk diff, which evaluates to 5 plus 1 asterisk 2 equals 7. Since the condition holds true, it means the missing number is in the right half of the array, so we update left to mid plus 1, which is 2. In the second iteration, we compute mid again as 2 plus 3, // 2 equals 2. Here, ARR, mid, is 11, but the expected value is 5 plus 2 asterisk 2 equals 9. The condition is false, indicating the missing number is in the left half, so we set right to mid, which is 2. At this point, left and right both equal 2, so we exit the loop. The missing number is calculated as ARR, 0, plus left asterisk diff, which is 5 plus 2 asterisk 2 equals 9. The output for this example is 9, as the missing number in the sequence 5, 7, 11, 13 is 9. Now let's consider another example, the array 1, 3, 7, 9. First, we calculate the common difference, diff. The length of the array, n, is 4, and the difference is ARR-1, ARR-0, // n equals 9 to 1, // 4 is equal to 8 // 4 equals 2. So, the common difference is 2. With this, we initialize the binary search variables, left is set to 0, and right is set to n1, which is 3. Now we begin the binary search process to find the missing number. In the first iteration of binary search, we calculate the middle index, mid, as left plus right, // 2. With left equals 0 and right equals 3, we get mid equals 1. Checking the value at ARR, mid, we find that ARR, mid, is 3, and the expected value is ARR, 0, plus mid asterisk diff, which evaluates to 1 plus 1 asterisk 2 equals 3. Since this condition is true, the missing number must be in the right half of the array, so we update left to mid plus 1, which is 2. In the second iteration, we calculate mid as 2 plus 3, // 2 equals 2. At this point, ARR, mid, is 7, but the expected value is 1 plus 2 asterisk 2 equals 5. The condition is false, meaning the missing number is in the left half, so we set right to mid, which is 2. With left and right both equal to 2, we exit the loop. The missing number is calculated as ARR 0 plus left asterisk diff, which is 1 plus 2 asterisk 2 equals 5. The output for this example is 5, as the missing number in the sequence 1, 3, 7, 9 is 5. For the final example, consider the array 15, 13, 9, 7. Here, the progression is decreasing, so the common difference will be negative. We calculate diff as r-1 error 0 / n equals 7 to 15 / 4 is equal to -8 / 4 equals -2. The common difference is -2. We then initialize the binary search variables, setting left to 0 and right to n1, which is 3. The binary search process will help us find the missing number in this sequence. In the first iteration, we compute mid as left plus right / 2 equals 0 plus 3 / 2 equals 1. Checking ARR mid, we find that ARR mid is 13 and the expected value is ARR 0 plus mid asterisk diff, which evaluates to 15 plus 1 asterisk dash 2 equals 13. Since the condition holds true, the missing number is in the right half, so we update left to mid plus 1, which is 2. In the second iteration, mid is calculated as 2 plus 3 / 2 equals 2. Here, ARR mid is 9, but the expected value is 15 plus 2 asterisk dash 2 equals 11. The condition is false, indicating the missing number is in the left half, so we set right to mid, which is 2. With left and right both equal to 2, we exit the loop. The missing number is ARR 0 plus left asterisk diff, which is 15 plus 2 asterisk dash 2 equals 11. The output for this example is 11, as the missing number in the sequence 15, 13, 9, 7 is 11. To analyze the time complexity of our solution, we start with the calculation of the common difference. This step involves using a simple formula, ARR-1 error 0 / n, where n is the length of the array. Since this is a direct arithmetic operation, it takes constant time, or O1. Next, the binary search portion of the algorithm is the most significant contributor to the time complexity. The binary search loop works by having the search space in each iteration, which means the number of iterations is proportional to the logarithm of the array's length. Specifically, the search space reduces from n to n/2, then n/4, and so on, until it narrows down to a single element. Within each iteration, only a constant amount of work is done, such as calculating the midpoint, comparing values, and updating the search bounds. Therefore, the time complexity of the binary search is O log n. Lastly, once the search completes, the missing number is calculated using a straightforward formula, ARR 0 plus left asterisk diff. This step also takes constant time, or O1. Combining these steps, the time complexity of the solution is dominated by the binary search, resulting in O log n. Now that we have broken down the individual steps, the overall time complexity of the solution is the sum of O1 for calculating the common difference, O log n for the binary search, and O1 for the final computation. Combining these gives us O1 plus log n plus 1, which simplifies to O log n. Moving on to space complexity, the memory usage in this solution is minimal. The input array is given, meaning it doesn't contribute additional space beyond what is already provided. The algorithm uses a constant number of variables, including n, diff, left, right, and mid. Since these require a fixed amount of memory regardless of the input size, they contribute O1 to the space complexity. Additionally, the solution does not utilize any extra data structures like lists, dictionaries, or recursion stacks. This means that the overall space complexity of the algorithm is O1, as it only uses a constant amount of space throughout its execution. When comparing this optimized binary search approach to a brute force method, the difference in efficiency becomes clear. In a naive solution, we would iterate through the array to check whether the difference between consecutive elements matches the expected arithmetic progression. If any inconsistency is found, the missing number can be calculated. However, this approach requires a single pass through the entire array, leading to a time complexity of O(n). The space complexity of this brute force method is O(1), as it does not use any additional memory. In contrast, the binary search approach significantly improves the time complexity to O log n, making it much faster for larger arrays. Importantly, both approaches share the same space complexity of O(1), so the key advantage of binary search lies in its logarithmic time efficiency. Let's now analyze the best, average, and worst cases for the binary search approach. In the best case, the missing number could theoretically be identified in the first iteration. However, since the binary search loop always continues until the search space is reduced to a single element, the time complexity remains O log n, regardless of when the correct value is calculated. On average, the binary search completes in O log n iterations, as the search space is halved in each step. Even in the worst case, the algorithm still operates within O log n time, as the number of iterations is determined by the logarithmic division of the input size. To understand this mathematically, consider that binary search repeatedly divides n elements in half, first to n/2, then to n/4, and so on, until only one element remains. The total number of divisions corresponds to the base 2 logarithm of n, or log 2, n. This is why the time complexity is O log n. Finally, the space complexity remains consistent across all cases, as the algorithm uses only a constant amount of memory, resulting in O(1). One common mistake is assuming the progression is uniform without verifying it. Just because the input looks like an arithmetic progression doesn't mean it actually is. If the input is invalid, such as not adhering to the rules of an AP, your solution could yield incorrect results. Always confirm that the input meets the problem's constraints before proceeding. Another issue arises with floating point arithmetic when calculating the common difference. For example, dividing by 2 to get the difference can introduce precision errors in some cases. Stick to integer arithmetic to avoid this. Additionally, skipping edge cases is a frequent oversight. Small arrays with only 3 elements or cases where the missing number is at the start or end of the sequence need to be explicitly handled. Inefficient approaches can also be problematic. A naive linear search might work, but it's not optimal compared to binary search, which is faster for this problem. Finally, modifying the input array, like sorting or altering its values, can lead to unintended consequences. It's best to work with the array as is to avoid side effects, especially if immutability is expected. Now, when tackling this problem in an interview setting, there are a few key insights to keep in mind. One important pattern is that the missing number splits the array into 2 valid arithmetic progressions, one on each side of the gap. You can leverage this property to narrow down the search space. For instance, using binary search, you can compare the expected value at the middle index with the actual value. If these 2 values differ, the missing number lies to the left, otherwise, it's on the right. This approach is both efficient and demonstrates your understanding of the structure of the problem. It's also crucial to clearly communicate your assumptions, such as ensuring the input is sorted and represents a valid arithmetic progression. Employers often check whether you validate these details. Additionally, discussing trade-offs during the interview can show depth in your thinking. While binary search is the most optimal solution, mentioning alternatives like the summation formula or even a simple linear scan can demonstrate your ability to evaluate different approaches. Lastly, always highlight the time complexity of your algorithm. For example, binary search achieves O log n, which is a significant improvement over the O n complexity of a linear search. To further strengthen your understanding, it's helpful to explore related problems. For example, LeetCode number 268 asks you to find the missing number in a range from 0 to n, while LeetCode number 448 focuses on identifying all missing numbers in an unsorted array. Similarly, LeetCode number 41 challenges you to find the smallest missing positive integer, and LeetCode number 1539 tasks you with finding the kth missing positive number. These problems share overlapping concepts and can deepen your grasp of similar patterns. Additionally, alternative approaches to solving the missing number in an arithmetic progression include using the summation formula. This method involves calculating the expected sum of the sequence and subtracting the actual sum to find the missing value. While simple, it runs in O n time and may lead to overflow with large numbers. Binary search, on the other hand, is more efficient at O log n, and compares the actual value at the midpoint with the expected value to narrow down the search. However, it's more complex to implement and requires careful handling of indices. Finally, a linear scan can be used to find the first deviation from the expected value, but this approach is less efficient at O(n), making it unsuitable for larger inputs. Great job making it to the end. To recap, we implemented an efficient solution to find the missing number in an arithmetic progression using mathematical properties. Remember, practicing problems like this enhances your problem-solving skills and prepares you for similar challenges. Thanks for watching, and don't forget to like and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!